Our experimental platform is the OmniOcta, a fully actuated 8-rotor omnidirectional UAV, capable of generating a 6-dimensional branch. Since the platform is fully actuated, the mapping from motor commands to the branch is redundant, meaning that infinitely many motor command combinations can produce the same branch. And, since the rotor teeth angles are fixed, the branch generation relies entirely on motor speed modulation. The goal of the OmniOcta is to perform a reference trajectory. Its execution is ensured by the following closed-loop control architecture. From the position, orientation, and the first and second derivatives errors, the controller calculates the desired branch. Then, an allocator computes the motor commands. It's important to mention that the motor dynamics is asymmetric. That means that the rise and fall constant time are different, due to the active braking capability of the OmniOcta's onboard electronic speed controllers. These constants are experimentally identified from the real platform. The allocator calculates the nominal unconstrained allocation from the desired branch. Then it applies a null space correction by adding to it the product of the allocation matrix null space and a variable x. As said before, there are infinitely many motor commands combinations. Every values combination of the variable x will preserve the desired branch, since it multiplied by the allocation matrix null space. This arises a question. How should x be chosen? We compare a QP-based control method currently implemented in the real OmniOcta, called motor-bound nullspace optimization. Since the unconstrained allocation neglects the actuator limits, the resulting command U0 may violate the motor bounds. So, to ensure feasibility, a quadratic programming is solved to enforce the actuation constraints. Here is a simulation experiment. The OmniOcta moves to a final position while performing a full rotation about the y-axis. Here is a real-world implementation, showing the OmniOcta performing a full rotation about the y-axis. Both simulation and experiments show that the motor-bound nullspace optimization formulation can induce oscillation in the motor commands. This behavior originates from asymmetric motor dynamics, where different rise and fall time constants cause a persistent mismatch between the commanded motor input and the actuated one. As seen in the real platform, the oscillations are higher to do additional and model dynamics. This leads to the need for an horizon-based method capable to anticipate motor behavior and modulate X accordingly. To mitigate this, we propose a short horizon shooting-based MPC framework operating at the control allocation layer. Our formulator incorporates the OmniOcta rigid body dynamics, the feedback controller structure, and the identified asymmetric actuator dynamics, while optimizing the null space allocation variables over a receding horizon for an online execution. We use constrained iterative LQR to compute feasibly and locally optimal control sequences. The optimization is performed over the prediction horizon, but only a short initial segment is applied before replanning. After executing the optimized command over this control horizon, the optimal control problem is resolved. The stage cost penalized variation in the actuation command to reduce chattering, and element-wise inequality constraints enforce physical motor limits at every prediction step. The control and sampling frequency is set to 500 Hz. Since the goal is to suppress oscillation caused by this mismatch between commanded input and actuated one, the prediction horizon must be chosen to capture the actuator transient response. Typically, a first-order system reaches 95% of its set point within 3 times tau. Accordingly, the prediction horizon is set equal to 4 times the worst-case actuator time constant, which in our case is the rise time constant. The control horizon is equal to 7% of the prediction horizon. This strategy enhances closed-loop robustness by limiting the influence of model mismatch and prediction error that accumulate over long horizons. Applying the optimized sequence over the entire prediction window without replanning can lead to divergence, as inaccuracies in the forward model cause the controller to overcompensate. Frequent reoptimization with early truncation keeps the controller responsive and prevents oscillatory or unstable behavior. In this video, the OmniOcta moves to a final position while performing a full rotation about the y-axis, following a 7th-order polynomial trajectory to ensure smoother velocity, acceleration, and jerk. This block compared the actual motor output variation for each actuator under both methods, confirming the substantially smoother motor command profile achieved by the proposed approach. The resulting reduction in oscillatory thrust redistribution mitigates excitation of the asymmetric motor dynamics with a consequent improvement of trajectory tracking performance, as shown in this plot. Specifically, the proposed method reduces mean position error by 60% and RMS position error by 68%. Orientation error also decreased, though inflated by 2-pi wrapping. But prior to this discontinuity, orientation errors are substantially smaller. This method achieved a smoother motor behavior and improved trajectory tracking performances. Future work will focus on optimizing its implementation for embedded systems, followed by validation on the real OmniOcta platform.